Welcome back, everyone. In this lecture, we're going to be taking a look at a coding example on a variety of datasets with dbScan. In particular, we're going to be exploring how dbScan compares to k-means clustering on some pretty unique datasets to get an intuitive understanding of the density-based approach of dbScan versus a distance-based clustering approach of k-means clustering. Let's head out to the notebook and take a look. Alright, here I am at the Jupyter Notebook with my imports, NumPy, Pandas, Matplotlib, and Seaborn. And what I'm going to do is read in a couple of different data files just so we can visually explore with a two-feature dataset how dbScan compares to something like k-means clustering. Let's go ahead and begin by checking out what I'm going to call a blobs dataset. We're going to say blobs is equal to pd read CSV, and then underneath the data folder it's called cluster blobs.csv. Then we're going to read that in. If you check out blobs as a data frame, it's essentially just two features, x1 and x2. And right now we're not going to worry about scaling or doing anything before we actually fit to that data set. Let's just explore what this looks like with a simple scatter plot. So we will say SNS scatter plot, state that the data is equal to blobs, and then we're going to say x is x1, and then y, this is just for plotting purposes, not a label, is x2. So what we have here are three different blobs on two features, x1 and x2. And keep in mind this is unlabeled data. We're just going to say x1 is a feature and x2 is a feature, and then we have these three blobs. So what we want to do is be able to understand how the clustering or dbScan is going to cluster these particular points, and you would expect it to come up with three clusters. And you can do the same thing with k-means, which we're going to be doing in just a second. Let's explore the other two data sets. One is called the moons dataset. So we're going to say pd read CSV, and then underneath the data folder there is cluster moons. And if you do a scatter plot with this one, in fact let's just see the head of it real quick. We can see again two features, x1, x2, and SNS scatter plot, data is equal to moons, and then x we'll say is x1, and then y is x2. Now this is a really interesting data set because what we have here are what is commonly called moon style clusters, where you have one moon kind of convex and one moon concave. Now you'll notice here that the actual tips of these moons are quite close to each other. So what we want to look out for are how is a clustering algorithm going to actually figure out the shape of these moons. From a human perspective, we can clearly see the two distinct features or kind of strokes of these moons. But a clustering algorithm may have trouble being able to tell the tip of, for instance, this moon over here on the left versus the center of the other moon, and vice versa. Finally, what we're going to do is check out what's called a circles dataset. So we'll say circles is equal to pd read CSV, and then I'm going to read in from our data folder cluster circles.csv, say circles head, and then we have x1, x2. Let's finally take a look at this scatter plot before we begin clustering. So we're going to say data is equal to circles, and then say x is x1 and y is x2. Whoops. Say equals x2. There we go. So now we have a really interesting set of data points here. What we can see is we have an outer ring or an outer circle and then an inner ring, kind of a donut shape. And again, from a human perspective, it's probably clear that we want to say that the outer ring is a cluster versus the inner ring. But can an algorithm actually determine that? So to actually kind of quickly explore this, I will create a function called display categories. And display categories is going to take in a model and then a data set. And what we're going to have it do is we're going to say that the labels is equal to model.fitPredict, which is going to fit to the data set and then predict the labels. Then after that, we're going to say show the scatter plot with data equal to data, x equal to x1, since all three data sets share the same column names, y is equal to x2, and what we're going to say is the hue is equal to the labels. And I'm also going to say the palette is equal to set1, just for some nicer color choices here to make it really clear visually what each model is doing. So what's going to happen is we're going to pass in a model like k-means or dbscan, pass in these data sets, circles, moons, or blobs, and then display the scatter plot that we saw here, except it's going to be colored by what each model thinks is the correct display or correct label. Let's start off with k-means since we've already studied it. We're going to say from scikit-learn.cluster import k-means, and we'll create an instance of the k-means model. So you can say model is equal to k-means. And to start off with blobs, what we can say is the number of clusters expected is 3. And then we'll say display categories, pass in the model, and then pass in the blobs dataset. So what that did is it took this model of k-means clusters, which expects 3 clusters. Remember, we have to define that before we actually run k-means. And then we have 3 distinct blobs. So obviously, we would expect k-means to really handle this task well. It figured out that these 3 distinct blobs should probably have 3 distinct clusters or labels. Now, what happens when we do something like the moons dataset? So I can change number of clusters to be equal to 2, because intuitively, we would expect this moon to be separate from this moon. So I kind of visually can already see that there should only be 2 particular clusters. So we'll come back here and rerun this so that we say to the k-means model, I only expect you to find 2 clusters. And instead of running this on blobs, we're going to run this on moons to see what happens. And this is the kind of effect we get. So recall, k-means clustering is using distance as a metric, and it's a main way of trying to tell which point belongs to which cluster, which means these points here, this kind of first half of the moon and this little tip of the other moon, they're actually quite close to each other in a distance space, in this n feature space, which is just 2 features, x1 and x2. And because we're really focused on distance here, we'll end up cutting these 2 data sets in half, so to speak. And you can see this kind of line that's being drawn here to get these points that are close to each other in a cluster, and these points that are close to each other in another cluster. And you'll see the same effect if we were to run this exact same model with the circles data set. So if you run that, you'll see again, it's using distance. So it's going to end up cutting these in half somewhere. And depending on your random start or random state, you may get the line or cut in half to show up somewhere else. So you may get kind of a split showing horizontal or maybe a diagonal, but more or less you should get some sort of effect where it's not actually able to determine the inner circle versus the outer circle or one moon from the other moon. Instead, it's kind of determining based off distance. And something to keep in mind is here we just have a 2-feature data set. But in real life, you're probably not going to be able to quite clearly visualize an n-dimensional feature set to get an idea if you have something like a sphere within a larger sphere. So let's take a look at how dbscan can actually perform, and we'll also note some important features of dbscan. Since we did mention it's kind of designed to look for outliers that don't belong to any cluster. So we're going to say from scikit-learn.cluster import dbscan. And I would encourage you to run help on dbscan and to check out the hyperparameters that we're going to be discovering in the next series of lectures. There are 2 main hyperparameters we need to be aware of. One is epsilon, which is the maximum distance between 2 samples for one to be considered as in the neighborhood of the other, and the other one is minimum samples, which is the number of samples in a neighborhood for a point to be considered as a core point. And we're going to talk about epsilon and minimum samples in much more detail in the next series of lectures. But just keep that in mind for right now. Okay, so let's go ahead and create a model, dbscan. And for right now, we're just going to leave it with its default values. And then I'm going to say display categories, and let's run it on blobs here. So if we say display categories, model blobs, notice what happens. It actually determines that there are 3 clusters, and then what's really unique about dbscan is it has this kind of special cluster code called -1, which are the points it determines to be outliers based off epsilon and minimum number of samples. So what's actually happening here is dbscan correctly identified 3 clusters and then decided that based off the density of these points and the values you gave for the hyperparameters, that all these points kind of on the edge of these blobs in red are outliers. And just based off a density metric, they're actually not close enough to the core of this blob to be considered a full point for that particular cluster. Now later on, we're going to discover how we could edit the hyperparameters and actually do a hyperparameter search to try to do something like get these outliers as part of the cluster. Because realistically, we probably want to determine these as 3 different clusters with no real outliers. But keep in mind, dbScan with some default values could actually refer to some points as outliers. And you know dbScan thinks they're outliers because it says their class or label is -1. Okay. So we have that caveat, but let's see how this performs on something like the moons dataset. So we'll say model is equal to dbScan, and what I'm going to do here is edit epsilon a little bit, and we'll talk about epsilon values later on, but I'm going to choose 0.15 for this particular dataset just so we can see how it's able to actually discover that based off the density and this particular value of epsilon, it can clearly determine that this moon is a different cluster from this moon. And what's really interesting is now it actually doesn't even identify outliers even for this point out here. And this is with epsilon of 0.15. And we'll figure out techniques to try to choose good values for the minimum samples and epsilon. But here we can see dbScan based off density is able to identify these unique shapes. And it's going to be able to do the same thing for circles. So if I swap out moons here for circles and run that, you can see it's able to identify the inner circle versus the outer circle. All right, so we can clearly see dbScan has some really interesting capabilities. And what we need to understand now are the hyperparameters that allow us to figure out what's the best choice in order to get these sort of determinations for labels to be done correctly. So what we're going to do in the next lecture is talk about hyperparameters in theory, and then after that we'll do some exploration of how we can actually code out a search for the best values of epsilon and minimum number of samples. Thanks, and I'll see you at the next lecture.